What I want to do today is hopefully help everybody get a handle on MATLAB and how to do things. And I'm going to first take you through, this is a problem that I gave you. Let me do this. Don't worry about that quite yet. Let me just, do y'all see what I posted, the problem where I had an inductor in parallel with resistor fed by a square wave current source. Do y'all see that, class? It's important you know how to do this. You're going to be expected to know how to program these type of problems and get meaningful results. So let me just show you what I mean. In the problem, it states that I have a current source here, some I of t, and then I have, I believe it's a resistor here of 1 ohm. You tell me if that's right or wrong. And then I have 1 ohm over here, and I have an inductor here, and the inductor has a value L equals 2. I'm just trying to.
So if the resistor at the top wasn't there,
Oh, it wasn't?
It's
It
just-
won't matter anyway, because it's a current. That's fine. The resistor there does nothing, if it was there, because you have a stiff current source. So I have a current feeding here, and what they wanted is the voltage, I believe, V of t here, isn't that right? Take a look at the problem. Oh, they want I? All right, that's even easier. I. They want I, call it L of t. Now, you're feeding the current I source, or I of t here, looks like this. It's periodic. This is 1 second, this is 2 seconds. And the height, is it 5 or what is the height? 5 amps. So this is a current, it's periodic, this is axis is time, and you can all get an idea what's going on here. If you want to, you can put a subscript S here, indicating it's the source, but it doesn't matter. Now, when you do this, first thing you need is a Fourier series representation of this. Do you all agree? I'm going to make sure if there is, I'll try to just keep it on this board. The way I'm going to do this is take one derivative, right? First I'm going to say this is in fact a Fourier series that's a summation of some, you can call it x of n or c of n times e to the j n omega naught t. N here goes from minus infinity to infinity. And that also means it's equal to simply x0 plus the summation from n equals 1 to infinity, right, of 2 times the magnitude of xn times the cosine of n omega naught t plus phase angle of x of n. You all remember that. This is the cosine series that we always use. When you're doing MATLAB simulations, use this, don't use this. This is a double sum, it takes more terms. You get the same information for halves. Everybody got that? Now, when I take a look at this obviously I could do the integration if I wanted x of n right here, couldn't I? But I'm not going to bother doing it that way. What I'm going to do is take the derivative, first derivative. I'm going to take the first derivative of this. I end up with a delta function here, and this would be simply I s prime of t. Delta function here of height 5, and then at simply 1 second I get a delta function with minus 5. At 2 seconds I get a delta function again of 5, and it repeats itself. Do you all agree with me, class? Making sure everybody sees all aspects of this. Agree? Now we take this and we get the Fourier coefficient for this series. I'm just going to call that x of n prime, because we've taken one derivative, 1 prime, 1 derivative. That means it's integral of 1 over t, in this case t is 2, right? Of the integral, now here's where I talk to you about this. This is a period, right? It has to be over a period. So slide the window down here so it captures these two only. Follow me on this? I don't want to be on the edges right here. It makes no sense because those are discount. There's no there's no easy way to do that. So just slide the window of integration here. So I'm going to go from really, I don't know, from minus 1/4 to 1 3/4 seconds. But that's just for, I guess, for the completeness. You kind of know where you're going. So what is this? Well, the weight on that's 5, right? This is the x prime of t. Then I put delta of t, and you don't have to be this careful with this. You know, you literally have a picture. You can do this in your head, more or less. And then it's going to be minus delta of t. Go ahead, what's the other term I need here? T minus 1, right? Minus 1. Then I'm going to multiply by e to the minus j n omega naught t dt. Does everybody understand what I've done so far and why I'm doing it? Right? I'm getting this, and where I'm going with this is divided by j and omega naught, right? To get back to the actual x of n, right? All right, so when I do that, what do I get? I'll put it here. My x of n prime is what? Well, it's going to be 1 over 2, right? Now just look at the first delta function. I'll put the 5 out in front. First delta function turns on at 0. What is e to the 0? 1. Put a 1 there. Next one, it's minus, where's the next delta function turn on? At 1, right? So it's just minus e to the minus j n omega naught. That's simple. That's x of n prime, just so you see every part of this. Now to get x of n, I divide by j n omega naught. Do you agree with me? So I divide this by j n omega naught. And now I have my x of n. I'm not quite done there with the x of n business. I still have to get x of 0. I can't get that from a derivative. Do you follow me? X of 0, just by looking at this as well. It's the average value. What is the average value? 5 all the way out to 1 second, 0 to 2.
2.5.
What? 2.5. Do you all agree with me? 2.5. So x of 0 is 2.5. Are we together on this? Now, now we need the transfer function of this. Now, do you mind if I erase this part right here? Okay. So now, the transfer function of this is, well, what is this? This is simple current division, isn't it, class? So the impedance of this would normally be j omega L. Do you agree? J omega. But now we don't have omega, we have n omega now. We have every single really harmonic. We have a different impedance. So here it's really j n omega naught L, or really it's just going to be j n omega naught times 2, right? I'm going to leave it like that. Or I could put L in there if you want. Doesn't matter. I can put L. So what's the transfer function? Well, my transfer function, h of n omega naught, is really equal to, it's going to be the ratio of output to input, right? When I look at this, the output is the current flowing through here. And if I have an input current of this, for current division, I take the opposite impedance over the sum. So that means this is simply 1 over 1 plus j n omega naught times L. And that would be current division, right? So now, to get the output, and I'm going to write it here, please write this down so you have this, and I'm going to do it. I know that now my IL of t will be equal to, and this is where it's important, first thing I have is going to be the average x0, right? This times h of 0. I'm going to get to this, talk about that in a second, plus the summation, please write this down, from n equals 1 to infinity, I'll get out of your way, of, now we have 2, that's the first thing. Then we have to put the magnitude of x of n here. Well, the magnitude of x of n is just the magnitude of that. You all with me in that class? Just the magnitude of that. Then it's times the magnitude, x of n is just that thing down there, pardon me. Times the magnitude of h of n omega naught. That's this, the magnitude of this, I'm sorry, I messed up before. Times cosine of n omega naught times t plus the phase angle of x of n plus the phase angle, right here, of h of n omega naught. So that's what it will be mathematically, and then we have to display it. Does everybody see what I've done? Give me a show of hands to make sure I know that you know. Now, the trick is this. When you're doing this, there's dots you need to put in with MATLAB, dot multiplies. There's a lot of strange stuff that I'm going to show you and try to bring out. What is h of 0? Just take a look at this. Is when n omega naught is 0, right? Just inspect that. What is it? 1. So that means my x0 is what? 2.5. Do you all see that, class? That is the current that would be going through there if it was DC. Do you all follow me?
Well, it would be the average value of the curve, I'm sorry, let me put the average value of that. Now, that said, now I'm gonna go program it, hopefully. And then I'm gonna take you through some things in MATLAB you need to be aware of. Everybody with me so far? Let's go ahead and just do this thing, and I'm gonna go here and show you what I'm doing. And, where's my, everybody have this here? Do y'all have laptops or not? Do you have a laptop? I mean, if you can, do you have MATLAB? Let me ask you this. Do you have MATLAB? Oh, can you open up MATLAB? Can you please get, I mean, because if you don't have it open, you're not gonna appreciate the things I'm trying to show you. That or look on somebody. I mean, move to with somebody that does have one that knows what they're doing. I'm really trying to help you guys. I mean, if you're masters in MATLAB, you don't need this, but a lot of you aren't. At least that's what I gathered from my discussions. So here, oops. This is the code, the basic code I gave you. Now what I'm gonna do is this. I'm gonna first comment out that H of n right here. And if you wanna comment something, you just put a percentage sign in front of it, and it acts like it's not there. It comments it out. Then I'm gonna go ahead and comment out this. That's the Y. And then I'm gonna take this out too. So I'm gonna first make sure that the original function, everybody listening now, did you have a question?
Just when you posted the homework, it only showed the question, nothing else would show.
This was something I sent you earlier. I sent you that in the link. Remember this thing I sent you for your base MATLAB program you had to change? Y'all remember that class?
Mm-hmm.
I gave, this is that program. The only thing I do is I adapt it to a square wave now.
Mm-hmm.
So I just changed the value of the coefficient. X of n becomes a different coefficient. It's this one on the board right here. Y'all see it? Just follow me on this. So for this one, let me put in L, not C, equals 2. Have L equal 2, and now the next thing I want to do is make sure I can replicate the square wave just by itself. And I'm just doing 2 periods. And hopefully I will. Oops, I did something wrong, and I think I know what I did wrong. Right here, plot T, next, oh, that's right. What didn't it like?
You were already using L.
Oh, yeah, I changed that. Actually, what I need to do is get rid of that. And this should replicate the square wave. I'll put a hardwire. Good work. Got an error. Oh. I gotta comment this out for 1 second. Now, I think this will work. No. Gotta comment that out. Sorry about that. I'm just trying to make sure you see a square wave. All right, now that replicates the original square wave. You gotta make sure you can do that first before you get the output. Follow me? That's the same square wave and it works. Well, and I had the coefficients, by the way, that I put in here. See this G of n? That is, I'm calling it G of n. That is that right there. It's 5 halves. It's A, in this case, A over 2. T is 2, so it's A over 2 divided by, tau in there too. gonna, okay, well, I'm gonna do this. I'm gonna reduce this complexity, I'm just gonna make this, this is going to be simply 2.5, right? Because that's A over T, and right out there, 5/2 is 2.5. Just put it right there, and then that should work. I gotta make sure it does that. Yeah, okay. So we replicate the original square root. Read everyone? Now what I'm gonna go ahead is put my second function, and that's this right here. And here's what I'm gonna do. I take the original one where I have magnitude of x of n and magnitude of x, or phase of x of n in there. Now I add, or I include the term magnitude of the transfer function here. And then I have to put the phase of the transfer function. You all see this? How many of you got MATLAB working on your code? Right? Do you want me to email? I can, if you don't have this code available, how about if I email it so you can, I'll just do this to the whole class right now. That way you'll have it. Boy, that's the problem. I forgot if it's spring like that. I think that's the address, but let me see. We'll try this. Let me know if you get, oh. Oh, this is it. You'll have the code in a second, I think. Tell me when you get it, so I know it comes through. You guys getting it? Just take that and paste it into your, to a window, an actual M file. Now, if you don't know what an M file is, how many don't know what an M file is? Just raise your hand. Anybody? Do you know what a script is in MATLAB? Everybody? In case you don't, the only thing you have to do is see this thing, new script, you type it, and that's a window that'll pop open. Now that thing you can run as many times as you want with this run button, and you don't have to retype your code in what's called the actual main window. But don't worry about that now, we'll get back to that. So for mine, I have to open my file. And this is what I had. Now I'm going to add on the part where I include the H transfer function, all right? For the transfer function, I call my transfer function H of n. Now you all see where I'm on, right there. I have it as 1. Now you see that dot after the 1? That's important because what it means, it's going to do element by element division, not matrix division. And I'll talk about more about that in a second. As a matter of fact, since probably some of you are wondering, let me show you what I mean by the difference between matrix, and I think I did this one other time, and really or term by term. If I have just A, and MATLAB's nice about this, make it 1s, make it 2 by 3, right? Then if I have B, and let B equal 2 1s, 2 by 3. If I take A times B, I should get an error because the 3 here doesn't agree with the 2 here. All right, now I should get an error, and I do. But if I do this, now this is individual element by element. I think I did talk about this, didn't I? Let's see what happens here. You see how it works? Now that's element by element. It's teaching each element of the matrix and multiplying it, like the 1, 1 is multiplied by the 1, 1 of the next. The 1, 2 multiplied by the 1, 2 of the next. It's element by element. Y'all with me on that? It's important. You'll see why this is important when you're doing a lot of bigger problems in scale. All right, now back to this, because I wanted to just tell you the difference there. Now I'm going to call this, my function right here is h of n, but instead of c, I'm going to put in just 2. It was meant to be L. All right, just 2, okay? Because that's the value of the inductance. Where else do I need that? I don't think I need it anywhere else, do I? No. And up here I have t is 2 and tau is t over 2, so I've specified that. The rest is verbatim out of there. So now I fire this, and I also want to plot this, so one other thing I have to do is down here, I create a vector, I just call this y. Before I had g of in for the individual terms of the actual cosine series. I have to sum those things. Just follow me on this one. So this is the same thing as the g of i's before that I had when I calculated the first Fourier series. Down here, instead of x, I call it yy, and this is going to be the current through the inductor, because I'm summing on the second term, which is the summing on m, you might say, that counts 1, 2, 3, 4 of the actual term by term counting of that. And then the output here will be given. Let me do one other thing. I want to just show you what that is and then plot. First, we're going to plot. No, I'm going to plot them both really. This is going to be p times x. Now, when you're plotting, if you want to plot two functions on top of another, this is one way. You put a comma here, then you have to repeat t again. It's always the horizontal axis. You put a comma and then y. So the first x corresponds to the actual source current squared wave. All right. The second term right here, y, corresponds to the output current through the inductor. I'm going to put them on top of each other, okay? And there's going to be an offset, because I did not include the actual average value. Now you see how this goes negative? This is the square wave, and this goes negative, right? All right. Actually, we have to add on the value and the average value, which is 2.5. Are you with me, class? So when I add on 2.5 to this, then you get this. All right. Now that's the actual output waveform, and I've got to talk about this for a second, because this is interesting. When I have an inductor here, what an inductor does, it has a very large impedance, think of it this way, for anything that tries to change fast. So when the waveform goes from here to here, the impedance is huge. It's basically not even in the circuit. Do you follow me on this, class? An inductor resists changing to current. And so what happens is, to get the initial value right after it transitions, take this out. Well, what would the voltage be here? It would be simply that current, right, times this resistance. If it's at a high state, it would be 5, wouldn't it? So take a look. Well, it should be 5. Did I get the right average value in there?
It's current, not voltage.
Wait a second, yeah. This is actually current, not voltage. There should be actually no current going through it at the transition, my bad. So when it goes from the high state to the low state, now this is the average current. And let me tell you one other thing about this. What you have basically is some average value here, the 2.5 that this thing is riding on. Now if I change the value of the inductance, and I'm going to do it in my program, you can see that as the inductance gets larger and larger, those ripples go to 0. Let me do it for you and you'll see this. This is basic filtering. Now watch what happens when all of a sudden I put this, and instead of 2, I make this inductance. Here's where I put the 2 right there. How about if I put this as LL, and I'll just put LL up here so I can get at it. And I'll make that equal to, say, 10. That's a bigger change. Those ripples should go down. Let's see. These ripples right here should go down. See how they're going? Now instead of 10, make it 100. So here, I'm gonna make this 100. And you're gonna see this become a DC, but it'll basically go to DC. Right. Y'all see how that's just the average value now? This is sort of, it kind of gives you a glimpse at how real filtering works. An inductor right here is going to be something where it gets rid of any kind of rapid changes. And then what it does is basically make this, if you want to think of it this way, if you do a source transform here, you could put a voltage of 5 volts in series with a resistance. You all follow me? Now you have a resistance in series with an inductor, right? Well, that, if you took, I'm taking the current, but if you took the voltage off that inductor, you would see that you would have a high pass filter. But what would happen to the actual current is it would be a low pass filter and just allow the average value. And that's why inductors are used to get rid of ripple. You all know that, don't you? You can use capacitors or inductors. If you put inductors in series, it gets away with ripple. Capacitors in parallel with the resistor will get rid of ripple as well. When I say ripple, the most common type that you run into is the 60 hertz that's annoying, so you can get rid of it that way. More on this later. All right, I wanted to get this to you. Has anybody tried to run the program I've sent you? Did it work? All right, did you modify it the way I did? How many modified? All right, if you've got your laptop here, I'm trying to do you a favor. Now, do you have questions about MATLAB? Any questions at all? Yeah.
So for your H, whenever I tried to enter, I found the absolute value of it, and then I found.
The phase is just phase. It's the word phase, and then the function.
Okay, so
You don't have to put a trigonometric function there. You just type the word phase and it'll give you the phase.
Okay.
That's the easy way. All right. I mean, the way I did it before, where I did minus the inverse tan of the imaginary over real. Well, I just did that to show you. In MATLAB, it's easy. Type phase, it's done. And it's in radians too. That's another thing too. You can work in degrees. I recommend as much as possible work in radians. If I put in COS, cosine of anything, it assumes radians. If I put a D, COSD, it's assuming the argument is degrees. Do y'all follow me in that, guys? And that's an important difference. There's a lot of other tricks, I'll tell you that. But you'll learn about these tricks as you need to program. Things with conjugates and stuff like that I can't talk to you about. All right, last thing. Any other questions about MATLAB at all? I mean, if I asked, and this is a question you're gonna get, if I asked, I changed this from a square wave to a triangle, and I want the output. Instead of maybe an RL circuit, like the one I have, suppose I have a RC circuit. The only thing difference is the transfer function, right? You could change the period. I could change tau, but fundamentally you have the structure to do any of that. Tau and all that stuff I put at the top, I don't even show it here. But all the constants that I'm going to be using, possibly using, I normally put clear all, close all, CLC. That gets rid of it, wipes the slate clean. There's nothing there that it can mess up with looking at a piece in memory from something else that's resident there. Because a lot of times when you're using MATLAB, you're doing 2 or 3 things, and you don't know if you used L 3 or 4 other places, and so now you clear everything. Now you put basic constants. I've got a lot here, but T is the first one, any periodic thing. After that, you'd have to put omega naught. You need omega naught right off the bat. That's a fundamental. Then you need tau if it's going to be something that's going to transition. So, and I always put it in terms of T. Next thing, amplitude. I had a -5 there for some reason, but you can change that, whatever the amplitude is. Then you go down and basically, I mean, I have some intermittent things, but now I talk about the actual time. So I linearly space points from -T to T, and I have L of them, and I have 1,000 points that I chop up the time domain into. evenly spaced. Now I calculate the values of h and g here in n, okay? Because they never change, they're not a function of time. Once I have those, then I go down here, and I'm gonna go ahead and say, well, I have both g of n and h of n, and then this is the actual cosine of n omega naught t. T, of course, is indexed from 1 to L, right? So I have to do that sum of this thing, where I'm summing all the terms from 1 to m, all right, all the actual count, the ones I'm counting in terms of the harmonics. And then I do the other one because I want the output. And, I create them here, I sum them here, and then I simply output them here with the average value. You can take a look at that. If you have questions, please don't be afraid to ask.
What is XXI here?
Well, if you look at this right here, I'm getting rid of n. N is like the first term, second term, third term in this Fourier series. Now I want to sum all of those for a given t, don't I? So I get rid of n, and now I have something that's just a function of t. It's I there, but I is indexing t. You got me on that, guys? And then you have to display it. So after I do this sum, now I have to display this, and it's not down, it's the plot function. By the way, how many know how to label things in MATLAB, axes and stuff? Just because you need to know this, let me just show you once. If you get your laptop, do it, and you'll see. Come down here to where it says plot. Let's just talk about some things you can do. One of the things you can do is hold on. I don't care about that right now. Now, grid on means it's going to put a grid. Oh, no. Chuck. Not that. No, not the dreaded dead battery. All right. Let me just try something. Let me run it real quick. You see how it has a grid? If you want to label it, I have X label seconds and Y label this. I just put the single apostrophe and put whatever you want to call it in there. One other thing you can do is you can do LaTeX stuff. If you don't know LaTeX, don't worry about it. But if you, this is if you wanted to say tau equals t over 2, you can do it with this, and it should catch it and put it in there. And you see that tau right there? That slash, spell out the Greek letter, and it'll put in the Greek letter. See how it's tau? You all with me on that? There's a lot of tricks like that. That's what I wanted to show you. Now we get into Fourier. We're done with Fourier series. Now we get into Fourier transforms. And I don't think anybody's had them. Was this helpful? I mean, how many got something out of this? I hope I answered your questions. Some of you probably know this already, because there are some people that are pretty skilled in MATLAB and Python in this class. My problem with MATLAB when I was first learning it, yeah.
I was just wondering if you know why, like when I run the program, it pops up figure 1, but it won't display anything. I don't know if that's like
It won't render anything?
I don't.
Could you see me after class?
Sure.
Because a lot of times, to be frank about it, it's something very subtle. You put a command in there, a symbol or something that you're not aware of causes nothing to be rendered, and I'll try to help you on that. But if you take that block program I sent you, you should be able to replicate everything.
That's what I did. I copy pasted the one you emailed me, and then I run it, and it pops up figure 1, but it's blank. Like,
All right.
It has something to do with like Flash Player or something.
This has nothing to do with this should be self-contained. You have the university version of MATLAB?
I'm on virtual classroom. It's like
Yeah.
virtual-
Does it work?
Yes.
Okay, see me afterwards, I'll try to help you. Now, this is going to be Fourier, it's Fourier transform, not series analysis. Now, first of all, remember with Laplace transform, if I had x of t and it went to x of s, the definition of x of s was the integral from 0 to infinity of x of t times e to the minus st dt. Does everybody remember that? That is the fundamental definition of the Laplace transform. The Fourier transform is very similar. Here, for the Fourier transform, it's F-O-U-R-I-E-R, Fourier transform. When I have x of t, now I get an x of omega. Not n omega naught, but x of omega. So both Laplace and Fourier transforms are for signals that are energy signals. It means they are not periodic. There is a trick you can do with Fourier series analysis where you can take the Fourier transform of a periodic waveform, but that's late in the class. For now, they're only energy signals. For instance, a lightning event looking at the current. That's something that's got possibly an infinite duration but finite energy, right? If you look at the waveform on, say, the output power from any of the dams, that's an infinite energy, finite power. Got me on that? Different. So this is for something that has no time limitations, but it's transient in nature. That's the whole idea of Fourier transforms and Laplace. Well, here's the deal. The Fourier transform is simply taking, remember here, S was equal to sigma plus j omega, right? Here, we replace S with just j omega, and we assume sigma is 0. That's the first step. So for the Fourier transform, instead of S, I use j omega. I don't put the j there. It's equal to the integral of x of t times e to the minus, now it's just going to be not S, but just j omega t dt. And the second thing that happens is the limits. You see how this limit started at 0 and went to infinity? We did not look at minus infinity, correct? Well, what we do here is we go from minus infinity to infinity. That means for all possible times, you have to do this integration. Can everybody get me on this? I'm going to do, right now, I'm just going to do one. And I'm going to show you Laplace and Fourier. So if I have x of t, and I let it be equal to e to the minus at times u of t, and I want the Laplace transform of that, how many remember that one? E to the minus at u of t. You should know the Laplace transform of this by heart, because on the final exam you're going to have to. It's what?
1 over S.
Thank you. 1 over s plus a. That's it. But remember, it doesn't exist for t less than 0. Understand that? Or it's 0 for t less than 0. Now, if you want the Fourier transform, this is x of s. If I want the Fourier transform, I simply take, because this one only exists for positive values of t, right? The only thing I do is take s and make it j omega. It's 1 over j omega plus a. That's x of omega. That's how simple it is. For things, now hear me, for things that do not have any non-zero values for the function below, or for t less than 0. Understand that, class? Now, if you have a function, if I have x of t equals the pulse function p tau of t, can we do the Laplace transform of that? What does the pulse function look like, guys? 1 from minus tau over 2 to tau over 2. This is 0 and this is t, correct? Well, it has values for non-zero for less than 0, right? You can't legitimately do the Laplace transform and have meaningful information because you're going to neglect the part that's at t less than 0. Do you understand this? Here you need to do a Fourier transform in its entirety. But here's the beautiful thing. If the function, a whole lot, about 99% of the functions we deal with, maybe 98%, usually have all their information that's non-zero from t equals 0 to infinity. So the idea is this: if you know the Laplace transform of something, good chance you know the Fourier transform by just taking s and replacing it by j omega. Does everybody hear me? Really important to get this. Now, for this one, this does have a Fourier transform. I'm going to do this because this is the beginning of Fourier transform pairs that you don't have with Laplace transform. All right, these don't exist. So please do this with me. For the Fourier transform of this function, right here, I'm leaving it at height 1, and this is p tau of t. It's this. I come over here and I say, well, the definition of the transform is the integral from minus infinity to infinity of the pulse function p tau of t times e to the minus j omega t dt. That's the definition, right? You put in x of t and integrate. Write it down. I want you to think about this. how am I gonna do this integral? Well, look at that function p tau of t, or rec t in the book. I don't like rec t, but I have my reasons. This is rec t over tau, right? Isn't that another way of writing the same thing? The book likes the word rec, I don't know why. It's not my book. I like, the pulse is the one I see in journals all the time. That's the reason I use it. So if I come down here, I want to do this integral. Well, the value of that function is either 1 or it ain't. It's either 1 or 0, right? When it's 1, it goes from what? Minus tau over 2 to tau over 2. And that's just 1, so get rid of it. Isn't that the integral we're doing, guys? That's it, right? The only thing I do, I adjust the limits, and I know it's a 1 there, correct? All right, do the integration with me. And I'll show you a couple things. Now, when I do this integral, what do I get? 1 over minus j omega, right, times e to the minus j omega t, where t goes from minus tau over 2 to tau over 2. Y'all agree with that? All right, let's go ahead and do that. So I have 1 over minus j omega, then I have this, e to the minus j omega tau over 2, minus e to the minus j omega tau over 2, correct? Please write that down. Just take a look what I'm doing. I'm simply plugging in the limits after I do the integration. Y'all agree with me? We'll make sure, I don't want to go too fast, and do not be afraid to tell me to slow down. Don't be afraid to interrupt me. Some students are just, they're taught that if you're interrupting a teacher, it's rude. It's not from, this is an exchange class, we're trying to learn. Yeah?
Wouldn't your second lead to the?
It is. It should be plus. I'm glad you caught that. That wasn't intentional. Occasionally I put them in intentionally to see if you're paying attention. That one was an accident. I am great at making mistakes. Y'all agree with that? Now, when you take a look, anytime you see exponentials, you think one thing, Euler's identity. So I'll put them up here again. You gotta know these real well. First one I like to put up is just e to the j theta. That's equal to cosine of theta plus j sine theta. And for completeness, you can put plus or minus and have plus or minus there. That gets rid of any ambiguity. The next one is like the cosine I like to put up next. Cosine of theta is e to the j theta plus e to the minus j theta over 2. We use that all the time. Third one is going to be sine of theta, and that's equal to e to the j theta minus e to the minus j theta over 2j. Remember, there's a j there. Agreed, class? Now, if you look at the top of this, I'm just going to structure it the way you should see it. When I look up here, I have a minus sign here, don't I? Well, if I bring a minus sign up, I exchange the position of these two. Do you agree with me, class? Right? Do you see it? I mean, if you don't see it, tell me, because my handwriting is lousy, but I gotta make sure everybody sees it. Look at that, man. So I'm gonna get rid of that and just get rid of that and make that a minus j. This is minus j. Now, I'm not done yet. What happens to this term right here? What does that look like? Look over there. Boy, it looks almost like a sine, right? Except I need to multiply the sine by 2j. Do you all see that, class? So I'm going to go ahead and do that right here. I'm going to take 2 times j times the sine of omega tau over 2. That's the argument right here. And it's over j omega. That's supposed to be a sine. You all agree with that? What's the next thing that's obvious? What goes away?
Get rid of J.
J goes away. J is no more, thank God. Now, I want to tell you why I want to show you this individually so carefully. Remember what the definition of sinc of x is. That's sine of x over x, correct? Y'all remember that? How many do? Y'all remember it or not? You don't remember sinc? All right. If you don't recall it, write it down. This function, sinc of x, if you have calculators, see if it has a sinc on it. It should. It is either going to call it, it's not a hyperbolic sign, it's SINC. It's used extensively in physics and engineering. And frankly, in mathematics, it's used a great deal in any type of information theory. Now, that is our definition of the sinc function. MATLAB's definition isn't that. In MATLAB, the sinc of x, this is MATLAB and several other places, sinc of x is actually equal to the sine of pi x over pi x. That's MATLAB's and a few other journals. But I gotta tell you why they do this. This is simply for display purposes. Because if you take a look at this definition, when does the thing go to 0? Well, when the sine term goes to 0, right? When's the first 0? When x is equal to 1. Sine of pi is 0, right? So what happens is all the zeros of the sinc function are in integers. Sine of 1 is 0, sine of 2 is 0, sine of 3 is 0, and the amplitude's decaying is a 1 over pi x. Do y'all follow me in this? But this function has the same exact value at 0. When x is 0, it goes to 1, as this function does. All right? The pi in here is simply for display purposes, to make it easier to plot and talk about. When is the first 0 on this one? When x is pi, right? At 0, this function actually goes to 1. You have to use L'Hopital's rule. You take a derivative of the top, derivative of the bottom, evaluate it at x equals 0. And the derivative of sine is a cosine x. Cosine of 0 is 1. Derivative of x is 1. 1 over 1 is 1. All right, now, when I take a look at this, I need to have this argument appear down here if I want to turn it into a sinc. Agreed? How do I get it? Well, I need a tau. What do? I put a tau here, and I put a tau here. It's that simple. Top and bottom, didn't change the value. I need a half down here, but I have a 2 up top, so I divide top and bottom by 2, and now I have this. Just take a look at that, people. Y'all see what I'm doing? Can y'all see it? I always worried when I can't see a guy's face because of that.
Yeah,
You can see it, all right? Everybody got that? Now, what is this? Well, isn't this really the sinc of omega tau over 2? And in fact, that's what the transform of this is. The transform of the pulse right here becomes simply tau times the sinc of omega tau over 2. That's it. Some of you are going to wonder, what does it look like? What does a sinc waveform look like? You're going to, because some of you don't recall it, I'm going to plot it up here for you. You know, it's nice that we do Laplace first, because Fourier pretty much a breeze for any function that's not 0. I mean, it has a value of just 0 for t less than 0. It becomes a breeze because you just take s and turn it into j omega. All right? So it's really trivial. But there are functions, and that was the first function, you don't have them. The next function that we get that you don't have is this function. It's called a triangle function. I use this symbol, and I put tau on here of t. What that looks like is this. If this is t, the triangle function of tau of t looks like this. It's a triangle, makes sense. It starts at minus t over 2. It ends at tau over 2. And remember, when the argument 0 is 0 there, there's the center. That's the high point. It's symmetric about that point. Now, the triangle function mathematically is usually given as simply 1 minus 2 times t, magnitude of t, over tau, times the pulse tau of t. And if you look at this, it works. Now look, that triangle function is 1 when t equals 0, correct, class? All right, put in 0 here. What do you get? 1, right? It goes to 0 at what? At t equals plus and minus t over 2, correct? Tau over 2. So if you put tau over 2 times 2, right, you get tau over tau is 1, 1 minus 1 is 0, right? All other values outside that range from minus tau over 2 to tau over 2 or 0. This is the triangle function. Are you with me? Now the triangle function, we're going to go ahead and, am I out of time? I am out of time. I'll give you what the transform is. We'll prove it next time. We'll talk more. The transform of this, the triangle function, let me put it right here. I don't know if they have this clearly, shown in the book. They don't, and remember, I try to give you a little picture. This is the triangle function, minus tau over 2 to tau over 2, height 1, and this is this function.
This goes to tau over 2 times the sinc, that's SINC, of sinc squared actually, of omega tau over 4. And I'll prove that next time. It's the sinc squared of omega tau over 4. Got it? We'll prove it next time. Again, this is another function that has values that are not 0 for t less than 0. So, yeah.
What will the quiz be on this Friday?
Oh, yeah. All right, for Friday's quiz, why don't we do this? Why don't we move the quiz till Monday so I can do more of the Fourier transform?
Can
All right?
I veto that? I have 4 tests next week. Please.
All right.
Yeah, well, I was thinking everything.
All right. I hear your cries. How about on Friday? We do it on a basic Fourier transform problem. Basic for. I don't want to do Fourier series again on this thing because I'm going to give you a MATLAB project for that. All right. I don't want to give it right now. But what I want to do is basic Fourier transform. So I'm going to think of the pulse. Think of this one. I'll give you like 5 or 6 other things to make sure you know the transform pairs of it, know how to do them, okay? All right, and see you on Friday. Thank you for that comment. I'm not